Hi everyone. So we're now going to do the more practical case in lesson 29, where we're estimating a population mean mu if sigma is presumed unknown. This is the more common and practical case. Now you might be wondering, did I waste your time back in lesson 28 then, if that was the less practical case, where sigma was presumed known? Not at all. I never waste your time. Not at all. Because if you understood lesson 28, and I hope you did, as best you could, then lesson 29 is fairly straightforward, except there are some differences. All right, how do we use t-distributions to estimate mu? So we're going to be using t-distributions, not the z-distribution, because there's a price to be paid if sigma is unknown. All right, so in this lesson, similarly to before, we will find 1 minus alpha confidence intervals, or CIs, for a population mean mu under these assumptions. And again, the most common confidence levels here, 1 minus alpha, are 95%, 0.95, 99%, 0.99, and in our example, we're going to see a 90% confidence interval, 0.90. Okay, and we're going to assume the following: that the population standard deviation is unknown. That's the key difference from lesson 28. We are finding confidence intervals for a population mean. That's a big predicate to all of this. And again, the central limit theorem has to apply, although we're really applying a variation on this. But again, when does the CLT apply? If the big daddy original distribution is approximately normal, or if the sample size is big enough, say bigger than 30. Again, the 30 is not from any algebra. It comes from practical observation. And if the sample size is large enough, then we don't have to rely on normality in the big daddy distribution. So again, these assumptions for the central limit theorem, they're the same as before, as for lesson 28, when we handled the z-distribution. Okay, so now, how do we construct a 1 minus alpha, that's the confidence level, a 1 minus alpha confidence interval, CI, for mu, a population mean? Well, when sigma is unknown, is given by the following. This here is the same setup as before. Same as before. The center of the confidence interval will be the sample mean, x bar. We're going to say that the population mean we believe to be the sample mean, give or take the margin of error, E, the exact same as before in lesson 28. But now there are a few differences in the formula for the margin of error, and that of course impacts this combined formula down here, which you can apply directly. And we're going to use the t-distribution on n-1 degrees of freedom, where n is the sample size. Remember that there's only one z-distribution. There's only one standard normal z-distribution, but we have infinitely many t-distributions indexed by the number of degrees of freedom. We want the one on n-1 df, where n is the sample size. This formula may change for different applications down the line in statistics. Now, what are the two differences you see between this formula and this formula that we had in lesson 28? What are the two key differences between this formula and ye old formula from lesson 28 over here? Well, they're both confidence intervals for mu, a population mean. They're both centered at the sample mean, x bar. But in lesson 28, we used a z-distribution. In lesson 29, we're going to use a t-distribution, namely the one on n-1 degrees of freedom. We still use that alpha over 2 notation. We're still splitting that alpha probability in half, symmetrically between these two tails. That stays the same, the subscript. Also, since we don't know what sigma is, like we did in lesson 28, we're now going to use S. So here are the two key differences from what we saw in lesson 28. Instead of a Z critical value, we're going to use a T critical value over here. For the same confidence level, this will be larger than its Z counterpart. We'll see why. Basically, it's because we're going to end up with a bigger margin of error. Instead of sigma, we had sigma in lesson 28. We're going to replace it with S, the sample standard deviation, because we've drawn the sample by now, over root n. So you can see that the CLT piece is still here, basically, except that we're replacing sigma, the population SD, with S, the sample SD. Again, let's review the two key differences between the lesson 28 formula and the lesson 29 formula. So again, in lesson 29, we use critical values from a T distribution instead of from a Z distribution, instead of from the Z distribution. And we're going to use the sample standard deviation S instead of the population standard deviation sigma, because we're assuming sigma is what in this lesson? We're assuming sigma is unknown this time. Whoops. Now, unknown. So we're stuck with S instead of sigma. But we pay a price for that. Because we're using S instead of sigma, that throws more uncertainty into our analysis. It throws a wrench into our analysis because the CLT wants us to use sigma. Well, we don't have sigma, so the best we can do is use S, the sample standard deviation. The price we pay for that is that we have wider confidence intervals because we're using critical values, CVs, from a T distribution as opposed to the Z distribution. And for a given confidence level, the positive T critical value will be larger than its counterpart Z critical value. Now, it's true, however, that as a sample size gets bigger, if n gets very large, then the number of degrees of freedom, n-1, gets very large for the T distribution, and you get something close to a Z value. So if you have a very large sample size, then this T critical value will be very close to the Z, and it's almost as if you knew sigma, because S will target sigma very well for a very large sample size. Before we do our first example, remember that the rounding rule will be the same. So we're going to round off this margin of error E. That's this whole guy here, right? The margin of error is this whole thing over here. We're going to round off the margin of error E. This is E. We're going to round it off to the same number of decimal places as the given value of the sample mean, x bar. So the same as for lesson 28. So if x bar is rounded off to 3 decimal places, we would round E off to 3 decimal places, or round up. Again, if we want to be conservative, we round up the value of E, the margin of error, to that number of decimal places. By rounding up, that tends to widen the resulting confidence interval, and we're playing it safe. We won't get sued. When in doubt, for a given confidence level, if anything, make your interval a little bit wider so that the actual confidence level is a bit higher. That's our way of playing it safe. So let's go to our example here. We're no longer talking about recalibrating an ice cream machine. That was kind of specific, wasn't it? We can do a more general example now. All right, here's our example 1 for a 90%, in this case, CI for a population mean where the population standard deviation sigma is unknown. We're finding a CI for mu where sigma is unknown. So let's say that you're a house assessor. You work for a real estate company. You assess house values in the lovely city of Springfield, maybe from The Simpsons. So you go around assessing their value. You want to know how much the average house is worth in the lovely town of Springfield. Well, is it lovely? Okay. So we're going to assess the average. We're going to do some assessing and try to estimate the average house value in Springfield. So who knows? Maybe you go to an old fraternity house. You might see a broken window here, empty beer keg there. maybe some guy lying down there, then the house may not be valued so much. And that might bring down the property values. But anyway, let's say that the houses in Springfield have values that are approximately normally distributed. What does this assumption allow us to do? It allows us to use what theorem, basically? It allows us to use the central limit theorem, or at least the variation we're going to apply in this lesson. 10 randomly selected houses are assessed. So what is 10? N equals 10. That's the sample size. But wait, it's not that big. It's not even 30 or 31. It's a low sample size. It's a small sample size. That's okay. Why is that okay? Because we're applying the central limit theorem. Granted, if your sample size were larger, then we would get better results in some sense. But in terms of our ability to apply the CLT, the central limit theorem, it's sufficient that we have a normal distribution to begin with, even though the sample size is small. The sample mean house value, so let's say that our assessor goes around to 10 randomly selected houses in Springfield, goes to an Excel worksheet, types in the 10 values for these 10 randomly selected houses in Springfield, takes the sample mean, and we find that the sample mean for these 10 house values is $350,000. And we can ask Excel to find the sample standard deviation, which is $25,800. You might remember in an old spreadsheet that we had, I wonder if I still have it. There's an old spreadsheet I had where I showed you how you could find the mean and standard deviation. Okay, like over here. All right. So here's the sample mean. Right. If these are 5 sample test scores, here's a sample mean. It's just the straight average function. Here's a sample standard deviation. Treating this as sample data. It's important we treat this as sample data. So sddev.s. Okay, we get the sample standard deviation. All right. Anyway, the assessor does that in his or her Excel worksheet or StatCrunch, whatever. And we're now going to find a 90% confidence interval for the population mean house value in Springfield. This is mu. When you write your final interpretation, right, then you should say the population mean house value in Springfield. As a shorthand, we'll use mu, the notation. And we're going to write the confidence interval in both this form involving the margin of error and also the form involving the limits. And we'll interpret. All right. The sample size is 10. Because we don't know the population standard dev, we're going to use the sample standard dev, S. I'll put that in red, bright red. This is S. We're going to use a sample standard deviation. So we're going to use the t distribution, not the z distribution. On how many degrees of freedom? Not 10. It's n minus 1, remember. N minus 1 degrees of freedom. If n is 10, n minus 1 is 9. So we want the t distribution not on 10 degrees of freedom, but on 9. You're going to use these hints. Basically, the positive critical value that we're going to plug in from this t distribution on 9 degrees of freedom is going to be 1.833. If you compare these critical values to the corresponding critical values from a z distribution, from the z distribution, if you're doing a 90% confidence interval where the z distribution is involved, then your positive critical value is positive 1.645. Notice that the positive critical value here for the same confidence level, 90%, I got to compare apples to apples. Notice here the critical value for this t distribution, 1.833, is a bit higher. In general, for the same confidence level, this positive critical value for a t distribution on any number of degrees of freedom, this would be higher than this z value over here. Although as the number of degrees of freedom gets large, as it approaches infinity, this will get closer to the 1.645 from z. Anyway, that was some theory. Again, it's good to state what mu is. Mu is the population mean house value in Springfield. The methods of this lesson apply because, first of all, we're finding a confidence interval for mu, a population mean. We're assuming that the population standard deviation sigma is unknown. So we're using lesson 29, not lesson 28. We're using a t-distribution, not the z-distribution. There's more uncertainty here. Because sigma is unknown, we resort to using S, the sample standard deviation, and that throws a wrench in. That throws in more variability. The CLT applies because we assume the house values were normally distributed in Springfield, approximately. So it was okay that the sample size 10 was rather small. We're relying on the Big Daddy distribution being about normal. Okay, again, the sample size n equals 10. That means that we're going to use the t-distribution on 9 degrees of freedom. We're also going to plug the 10 into here, this radicand. The sample mean x bar is $350,000. The sample standard deviation, we need that this time. We assumed it was $25,800. That was from the Excel spreadsheet or StatCrunch. Okay, so the margin of error, this is from the formula I showed you earlier. The positive t critical value, that's from the hint. For a 90% confidence interval, t-distribution on 9 degrees of freedom, we want the 1.833. That's the positive critical value we want. That goes here, the 1.833. The sample standard deviation from our Excel spreadsheet was $25,800. Sample size was 10. The 10 goes here, not the 9. Work this all out, we get about $14,955. We'll show how Excel can spit this out for us later on. So a 90% confidence interval, this is the margin of error for a 90% confidence interval. For a 90% confidence interval for mu, we take the sample mean, which was the $350,000. We take the sample mean, we plug that in here. The margin of error, put that in purple, the margin of error is about $14,955. All right. Well, we calculated up here. It goes here. Okay, E was about $14,955. That goes here. So this is one form for the confidence interval. We're saying that the population mean with 90% confidence, this population mean is about $350,000, give or take about $14,955. Okay, what if we actually want the limits of the interval? For the lower limit, we take the sample mean and subtract E, so we take the minus case, we get the lower limit, $335,045. For the upper limit, that's the plus case. The sample mean plus the margin of error gives us $364,955. The lower limit goes here, always. The upper limit goes here, always. Separate them with a big comma. Interpretation. We are 90% confident that this interval here contains the basically mu, but you should write it out for the layperson, contains mu, which is the population mean house value in Springfield. We're 90% confident mu is somewhere in here. So in the mid 300,000s, basically, in dollars. All right. And again, see, this interval is a bit wider than it would have been if we had used the z-distribution because, see here, we're assuming that we don't know sigma, so we have to use S. We have to use t critical values, and that leads to a bigger margin of error, so this interval is more spread out. Okay, later on, we're going to talk about tests for other parameters besides mu. In our next video, I'll show you how to use Excel to come up with these things.